Hi friends, welcome to my channel. Let's have a look at problem 713, subarray product less than key. In this video, we're going to give a treatment based on the two-pointer sliding window trick again. First, let's look at the statement, then we do the analysis, and finally we share the code. First statement, given an array of integers called nums and an integer key, return the number of contiguous subarrays where the product of all the elements in the subarray is strictly less than key. So here are two examples. So in example 2, the k equals 0 and nums are all positive numbers, so the output is 0. And in example 1, so the output is 8, and you can specify these things in the explanation. And before we do the analysis, let's look at the constraint. First, the length of nums is bounded above by 3 times 10 to the power of 4. So this is actually a decent large number, right? So secondly, the elements in the nums is not negative. First, this is actually important for us, and it's bounded above by 1000. So the third constraint is that k is bounded below by 0 and bounded above by 10 to the power 6. So 0 is a possible value for this k. However, because the elements in the nums list is positive, so if k equals 0, so we are sure there are no such subarrays with product being 0, right? So k equals 0 is really an edge case. With that said, we are ready to do the analysis. So first, our treatment is the standard two-pointer sliding window trick. So here the idea is the following. So for each right index r, we want to find the smallest index L, which is less than r, such less or equal than r, I would say, to make it more precise, such that the product of nums L plus 1 up to nums r is less than k. So I'll call this equation equation or inequality star. So then any subarray starting from some index I with I is bounded below by L and bounded above by R. So and ending at index R satisfies the problem requirement. So the contribution is R minus L plus 1, right? So counting all valid subarrays ending at all the indices R gives the full result. So next, we want to explain why the two-pointer sliding window method works here. So actually, it's due to the monotonicity. So given R, let L be the smallest index such that star holds. Then we have, if we make R larger, then the corresponding left pointer L should be no smaller than the previous one. So this is actually very important for the two-pointer sliding window trick to work here. The consequence of this monotonicity is that the consequence of the this is the repetition. So the consequence is that when we iterate for R, so we can use the previous state of L, and we do not need to start over again from the very beginning. In other words, start over again from index 0. So before we write code, here are comments and extensions. So the extension below is actually very natural. Can you count the number of subarrays such that the element product is larger than k, right? So this is the extension. So you can take the above idea or take the code we are going to share to do this, to achieve this. The comment is the following. So as the elements in the nums list is all positive. So here let's change it to the R. So we could actually consider the following, the below list. So nums. So we are going to apply the logarithm function for the elements in nums. Then this problem actually is transformed to consider finding the number of subarrays with sum less than the logarithm of k for when k is greater than 0. as we mentioned, k=0 case is an edge case. So this still can be treated by the routine two-pointer trick, or we could use partial sum plus binary search treatment. However, we didn't do this here. The reason is that the function logarithm changes the type of items in the original list. So actually it's not very natural for this problem in such a sense, but it's still doable. So with that said, let's look at the solution formats. So I'm going to write the two-pointer sliding window method using two formats. One is using the for loop, and the other is using a while loop. So essentially the same, but it's good to know the variants of the representations of such trick. So first, I'm going to treat the k=0 case. If k=0, we are going to return 0 due to the problem assumption, because all the elements in nums is positive. So once this edge case is treated, so let's call it step 1 edge case. So we're going to run the two-pointer sliding window method. So for this, we can first do some preparation. So let's see, we initialize the count variable result to be 0. And then we're going to get the length of the nums just for convenience. And we need to track the product. So we're going to have the product to be 1 at the very beginning. So left hand pointer to be 0, and the right pointer to be 0 again at the very beginning. So but if we want to use for loops, so we can do this for r in range m. So this way, when we look at nums, the element at index r, so we're going to amplify the products by product equals product times nums r, right? Then inside this for loop, I'm going to, for this fixed r, I'm going to find the smallest possible L such that this equation star holds, right? So this is a while loop. So while product is larger than or equal to k and L less or equal than r. Then what we're going to do is to shrink the product. So product interdivision by the left end, that is nums L. As long as this product is no less than k, we're going to do this. So this division corresponding to move the left to the right by 1, right? So after we exit this while loop, there are two possibilities. First, the product is less than k, and L still less than or equal to r. Or, so L is larger than r by 1, right? So both cases, we can do this. Result increment is r minus L plus 1. So if L is ending at r plus 1, so this contribution is still 0. It does not affect the final counting. So once this is done, so we find the contribution of possible subarrays ending at index r. Then we are ready to return the result. Let's see, this is step 2, so two-pointer trick. So next we are going to do the return. So we're going to return the result state. So that's actually one solution format. So let's do a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So next, I'm going to copy this solution format, and I will say this is version 1, and I want to write a for loop format of the two pointers. So here k=0, this is the edge case, and for now, let's also initialize a right pointer r. So I'm calling it 0, and then, well, r less than m. What we're going to do is do this product amplified by r, then this while loop. So after this result update, so I'm going to write r plus 1. So the reason is I have found the possible contributions of subarrays ending at index r. I'm going to towards the next index. So this is another format. So then essentially the two formats are the same. However, it's good to know the two variants or representations of the two-pointer sliding window methods. Depending on our problems, so actually one format can be more convenient than than the other. So with that said, let's first do a check. So here it should be 0, not a hyphen. So yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So with that said, I guess that's about it for this specific problem and for this video. So here actually we do the return. So that's it. Thank you.